welcome. Hello. My name is Matthias Scheffler, and it is a pleasure to start this series of tutorials with a general introduction and overview. The primary group of attendants today is the FAIRmat community. FAIRmat is a Germany-based international activity, and I will explain later what it is and what it does. The internationality is reflected by the fact that we have many people in the audience from many countries of this planet. There have been well over 40 countries, people from 40 countries registered, and as far as I've seen, actually the audience already looks like that. This international aspect is also reflected by the fact that today's and tomorrow's tutorial is being joined by a school and workshop at the East African Institute of Fundamental Research. The leading person of this school, the director of this institute, Omololu Eken-Oyo. And we have a group in the audience that is learning the FHI aims ab initio material simulation package. Now, the goal of these tutorials, you can say the goal of FAIRmat, is to bring material science to a new level of research by enabling new types of studies and new types of data analysis, and by advancing the present scientific culture. Now, my talk will explain what I mean by this ambitious statement. The key, or the first necessary step, is sharing and verification of research data. Markus Scheidgen and I will explain what this means on the long run, and you will also see how the FAIRmat activities can support your research work already today. Now, FAIR. By now you have heard this and read this word several times, and I guess that many of you know the meaning of this acronym. Many, but maybe actually not all. So let me very briefly explain. The F in FAIR stands for the request that research data should be findable. This is significantly more than the request that a publication should be open access. Making research data findable means that all data, not just the few figures and results that enter the publication, should be published at a data repository. Making data findable also includes the many details of the experimental setup, the characterization of the sample, and it includes the many data that were measured or calculated, but are finally not used for the very focused publication. And research data should be stored in a way that they are accessible. This is the A in FAIR. For sure, data should be accessible for the next generation of students and postdocs of the research lab where the study has been performed, but some delay that is an embargo period may be fine. Bureaucratic rules must be avoided as much as possible. The new level of science is enabled only if these findable and accessible research data are interoperable. This is the I in FAIR, and this is very difficult to achieve, but it's a very important request. Let me therefore explain that a little bit more. What is interoperability? It means that if, say, someone is doing a measurement, just one specific example for, say, on titanium dioxide to learn something about vacancies and bolarons. And another one is looking at titanium dioxide because this person or this group is interested in optoelectronics of this material. And yet another one is interested in doing some electron microscopy measurements because the group is interested in pigments and colors. Or someone is interested in heterogeneous catalysis because titanium dioxide is a very important support material. If every group on this planet would put these data on their own storage platform, the way they were measured or calculated, this would probably not help very much. That is, the data were only useful for other experts from the same area, photoemission or electron microscopy or density functional theory or catalysis at best. But it's very likely that even these experts will not understand what sample was actually measured or what approximation was used. So making data interoperable means that the data are fully described or characterized with well-defined and well-documented metadata. Only then experiments or calculations can be reproduced by others. Only then the data from different groups can be combined for a new study. And this is already actually the R in FAIR. Research data should be reusable and repurposable. Then people can not only use the data to repeat what was done, but they can also use the data and address a different purpose. And one can combine results from different studies. This is the standard definition of FAIR. And this is also our understanding in FAIRmat. But we are looking somewhat forward, and we also interpret the acronym such that research data should be findable and ready for further analysis by artificial intelligence. This means the data should be fully characterized and presented in a way that people from the field of AI or machine learning can use them for a continuative study, even if these other researchers don't understand the details of the actual measurements or computations. Research data should be findable and AI ready. Now, this is an enormously complicated project, but it is important. Before I go into this, here is actually just a schedule of today's FAIRmat hands-on tutorial series, but I don't like really to go through this in detail. Let me just note the very first three things. So we are in the middle of starting in the first one, which then continues publishing and exploring data with NOMAD by Markus Scheidgen. Next month, we will talk about electronic lab notebooks, and then we start talking about artificial intelligence, and there is much more coming. I ask you to visit our website to read the schedule with more leisure. This is the web page here. And just keep in mind that the typical schedule of this tutorial series is that we meet the second Wednesday of the month at 3 p.m. European time with an overview talk, which is then followed by the hands-on tutorial. And this continues on the next day, Thursday, with 2 sessions at 10 a.m. and at 4 p.m. So what is the motivation and basic concept of FAIRmat? How can we achieve what I have mentioned? And what is the concept of this tutorial series? FAIRmat is building a research data infrastructure for material science and the chemical physics of solids. So it's not a research project. And you may ask, why are we active in building an infrastructure? This is not a rewarding activity on the short term. The motivation is that the large amounts of data that are produced every day in our scientific fields represents an important raw material of the 21st century. You can say a gold mine. This gold mine is, however, of little value if these data are not comprehensively characterized and made available. Thus, the motivation is to refine this feedstock, to turn data into knowledge and value. The structure of FAIRmat is sketched here. Different areas have different colors. In yellow, we have area A, the synthesis of materials, and this is led by these 3 people you see here. In short, area A aims at making sample synthesis reproducible, finding hidden synthesis parameters, accelerating the development of novel materials by devising synthesis recipes. Then in green, we have the experimental material science. This team shown here so these are the leaders, but then there are many more people who are doing really a lot of work. This team will implement FAIR data principles in key experimental condensed matter physics disciplines. They will start with 5 exemplary experimental fields: electron microscopy, core level spectroscopy, angular resolved photoemission, optical spectroscopy, and atom probe tomography. And from there, they will move on to other methods. The key issue in the past months was and is the crucial discussion and decision about electronic lab notebooks. In March, that is in the next tutorial, these three people and other FAIRmat co-workers will share their experience on ELNs. So if you are an experimentalist, I think you must not miss the next tutorial. Computational material science is area 8 in turquoise. We started with this already actually 8 years ago. So that is to some extent a little bit like a forerunner. And it was established at the European Center of Excellence, NOMAD. This NOMAD work is now integrated into FAIRmat. And the previous Center of Excellence work is being significantly enhanced in terms of services by adding recent ab initio advancements, by adding classical simulations, multi-scale modeling, and excitations. Area C will also prepare the incorporation of other theoretical methods into FAIRmat. Now, one of the services provided by Area C is data analytics and artificial intelligence. And in the tutorial in April and June, Luca Giringelli, together with other colleagues, will present the NOMAD Artificial Intelligence Toolkit. Going to Area D, that is in blue, they address all the different issues in building and managing the digital infrastructure. Area D will lay the foundation of a federated research data infrastructure for the wider condensed matter and chemical physics community. And today, Markus Scheidgen will present some of this work. Area E demonstrates the functionality of the FAIRmat data infrastructure and possibly identifies weaknesses to be improved. It will also show how the developed tools will support the research of the various subcommunities. Area F reaches out to the community, provides ample information and training, fosters awareness for FAIR data issues, and returns suggestions to the other areas for improvement. Today's tutorial obviously is such Area F contribution. In the leadership, you see that the position of the coordinator is still open, so please spread the word. Area G is dedicated to coordination and administration issues, both within FAIRmat and within the NFDI. The chairperson of the whole operation is Claudia Draxel from the Humboldt University. You've seen already many people on the previous slides, but there are many more, and you can find them on our website. But in fact, you can also see them here. These are the area leaders in the second line, the task leaders, and then in the last two lines, the so far employed people. This is a very motivated, hardworking crowd. It's really, they all understand, in fact, what the potential of building the structure will be at the end when it works the way we hopefully it will work. Now, let me now sketch the history of material science, also to explain, in fact, my title of the talk. So how was and how is material science developing? And where is it going? Why is FAIRmat, why are we saying that FAIRmat is opening new horizons for material science and for materials research? So let me briefly discuss the past and present upcoming research paradigms. With this, maybe just a clarification. A paradigm is not just the introduction of a new method or concept. It is a new way of thinking. Sometimes it is argued that with a new paradigm, the previously established understanding is no longer valid, but this is not true here. I think not true in research and science. A new paradigm in basic research means new, important, and complementary way of thinking. And let me go through this to explain that. And you see here on the bottom a timeline in say 1600 up to say nowadays. Typically, science advances go together with the availability of new methods. Indeed, this is also behind the different steps here. Material science started about 5,000 or 4,000 years before the Common Era, when the Stone Age advanced. So somewhere here, when the Stone Age advanced to the Copper and Bronze Age. This was when mankind was able to control fire. This was, I would say, the starting of what we nowadays call metallurgy. So this is the advent of experimental material science, 5,000, 4,000 years before the Common Era. And then it took quite some time, up to 1600, that the next paradigm, the next way of thinking really started. Towards the end of the 16th century, scientists began to describe physical relationships by mathematics, and analytic equations became the central instrument of theoretical physics. Well-known names are Tycho Brahe, Galileo Galilei, Johannes Kepler, Isaac Newton, Gottfried Wilhelm Leibniz. The latter two, Newton and Leibniz, developed the concept of the mathematical differential and derivatives. Thus, analytical equations became the central instrument of theoretical material science. It was and is still assumed that nature and what we observed can be described by differential equations. This new way of thinking, the second paradigm, is symbolized here by the Schrödinger equation. Needless to say, the first paradigm, the empirical and experimental sciences, did not become obsolete, but theoretical physics represents an important complementary methodology. Since the 1950s, electronic structure theory was advanced for materials by John Slater. The Monte Carlo method was introduced by Metropolis et al. Alder and Wainwright and Raman introduced molecular dynamics. These are the key methods of statistical mechanics, and Hohenberg and Kohn and Shem laid the foundation of density functional theory in the mid-1960s. These developments define the beginning of computational material science, what is nowadays considered the third paradigm, because herewith computer experiments were introduced. That is, simulations were introduced whose results are often treated and analyzed analogously to those of experimental studies. Today, big data and artificial intelligence revolutionize many areas of our life, and material science is no exception. This fourth paradigm, we argue that big data reveal correlations and dependencies that cannot be seen when studying small data sets. Now, this vision was first described by Jim Gray, a scientist from Microsoft Research at a Microsoft workshop in 2007. The content of the workshop was then published. It's actually worth reading. The fourth paradigm, data-intensive discovery. This was actually the last big thing Jim Gray has done. 2 weeks later, he disappeared with a sailing boat at the Pacific Ocean. An important difference of this to the second paradigm is that we now accept that there are many materials properties, for example, patterns and correlations in big data, that cannot be described in terms of a closed mathematical formulation or a meaningful analytical equation, as they are governed by several intermingled theoretical concepts and multi-level intricate processes. As a consequence, such patterns and correlations represent advance in knowledge, but they do not necessarily reflect understanding. And this is very different, obviously, to the second paradigm. If you like to read more, you can find this more really in this publication by Claudia Draxel and me in this handbook of materials modeling. The fourth paradigm of materials research will change the way how science is done today. And This is the reason why in FAIRmat we like to present data as findable and AI ready. The NOMAD Center of Excellence was actually very active and influential in this regard, but they were focusing on computational material science. Now we are looking, of course, much broader to all the experimental and synthesis aspects. Let me elaborate on that. Considering the 100 atoms of the periodic table of the elements and all possibilities of mixing these atoms in all possible structures and unit cell sizes implies that the number of all possible materials is practically infinite. This implies that it is very likely that materials exist that we don't know so far and that have novel properties or performance in their function that is better than that of the materials we know today. Or it may be that some known materials have properties that we have not recognized so far. So how can we find these exceptional materials? Now we can get important information, necessary information by high throughput experiments and computations. But in view of the sheer size of the chemical and structural space of materials, this direct information will remain very insufficient. The daunting challenge for artificial intelligence, for material science, is that this practically infinite space, in this practically infinite space, the interesting materials are very rare. The interesting materials, that is materials with a high performance function, are statistically exceptional. A route towards solution is to create maps of materials, properties, and functions. These maps rely on the knowledge of the appropriate coordinates, the x-axis here and the y-axis, called here descriptor 1 and descriptor 2. These are physical parameters that are initially not known. Only if we have found the appropriate descriptors, we may discover such a map where in relatively small areas, there are materials that are good superconductors, and in other areas, materials for photovoltaics and so on. Obviously, at first we need data, and then we can, with artificial intelligence, try to find these x and y axes, the descriptors. Finding data, a critical component of that, but that means actually for FAIRmat, this is sketched here. The entrance level for new data, and this is actually how we started with NOMAD. So much I'm saying is NOMAD, but FAIRmat has the same structure. The entrance level is here. At first, and here we accept 40 different software packages in the field of first principle electronic structure theory, molecular dynamics, and increasingly also from force field codes. These are very different packages with very different, say, units and definitions. In order to be able to judge the value and the range of applicability of the data, we request that the full input and the full output files are given. Importantly, we asked for the data in a way they were produced by the employed software, because we don't want that the user has work. The user has not to do any work. She or he just uploads what the code had produced. And we will then process or parse, convert, and normalize the data. And this is called here processing. And the converted data, only these can now be understood by nearly everyone. Only the converted data, that they are stored in the NOMAD archive. Repository is not fair because hardly anyone will understand what is there, but repository and archive together are fully fair. We started with this in 2014, and now the size of the repository and archive are quite significant. If you can read that, there are nearly 110 million results and 12 billion quantities in the archive. Data in the repository and archive are stored for at least 10 years after the upload. The data can get a DOI, so they are citable. More information you will get in the upcoming tutorial by Markus. NOMAD is the biggest data store in computational material science, and we are in close contact with all the big databases in the US, AFlow, OQMD, and Material Projects, and more. There's an automatic synchronization that fetches their data, stores the raw data, and then converts them to the archive. So far, NOMAD is focusing on computational material science but this is changing. We just started with integrating data for material synthesis and experience. There is a lot of information in the archive, and one can look at it via the NOMAD encyclopedia, which you see here, or the artificial intelligence toolkit. This, in fact, here is the encyclopedia webpage. Lauri Himanen will present it in a tutorial in July, but you can, of course, use it already now. One clicks at a periodic table to select the element which builds the solid you are interested in. And then the system offers some choices. And finally, you may get a page that looks like this. You can see the structure, which you can also turn and look from different perspectives. You get the band structures, here it's spin polarized, you get the density of states. In many cases, there are also phonons. If they are available in the archive, there could be specific heat and more. And here you see the landing page of the NOMAD Artificial Intelligence Toolkit. Here you can query the archive. You can also look at tutorials sorry, to learn about methods. And you can, so you have tutorial videos to learn about different AI methods. And you can use Jupyter notebooks, which are offered to reproduce published results. The idea is that your user can use these notebooks and then, in fact, change the notebook towards their own research. There will be 2 tutorials on the AI toolkit in our tutorial series in April and June in June. So let me summarize in 3 final slides what I wanted to tell and where we see the scientific potential and impact of a fair data infrastructure. Data, findable, AI-ready data, enable new levels of research. That does not come for free. It comes with a lot of work. We need fully characterized data. We need to develop handbooks. We need to define metadata and ontologies. With handbooks, I mean, we need to define what type of information users should provide so that the data can be used in an interoperable way. If this is done, we have succeeded that published results are reproducible. Now, of course, that is a standard scientific request that data should be reproducible, but often in material science and synthesis, this is not the case. We really want to improve on that. Identification of materials, genes, and rules are possible. And with this, I mean basically what I said before when I said this creation of maps of materials properties. The descriptors which enter these maps contain very basic physical parameters, and they are like genes in biology. These are basic parameters which are not identify exactly the mechanism, but they correlate with mechanisms which could actuate the process you're interested, could be also hindering the process, it could just facilitate the process. Like genes in biology, different genes defining the maps will in fact telling you, and of course, that gives you some descriptions, but that does not give you laws. It gives you some descriptions, and we call this rules. That will enable us to get novel materials discovery. I think it also implies that we niche the scientific culture. My request, or our request, is that the publication of comprehensively annotated data has a higher value than most present-day publications. It's an enormous work to really present comprehensively annotated data, and we should acknowledge that at the moment, publishing things which sometimes are not well annotated, together with, let's say, a fishy interpretation, is not really, I think, what brings science forward. We should appreciate that comprehensively annotated data is a huge step forward. And I think about that when I'm saying that about an example of Tycho Brahe and Johannes Kepler and the NOMAD Kegel competition. And let me just actually mention or tell what I mean by this. Tycho Brahe was probably the best experimental astronomer of the time in the late 1600s. but he didn't want to share. He had the best data, but he wanted to interpret the data himself. Johannes Kepler was probably the best mathematician at that time, but he couldn't get the data. Now, only when Brahe turned 54 years old, he invited Kepler to become his assistant. So Kepler could learn a little bit about the data. A year later, in fact, Brahe died. And that was a big chance for Kepler. He had understood how the data are structured and he could get all the data. That was maybe not completely legal, at least it was discussed. But he got all the data, and then in the years later, he could develop his rules of his laws of planetary motion, the Kepler laws. Later then, Newton could, based on the Kepler laws, develop the theory of gravitation. So I think we should acknowledge that having fantastic data, as Brahe had, is important by itself, but accept that there may be someone else, like a Kepler, who can really use them, and let's share data more efficient than these two guys have done it. We have used that concept in what is called the NOMAD 2018 Kaggle competition. So let me just tell you, Kaggle is a platform on the internet for, say, the machine learning community. Meanwhile, it has been bought by Google. And so what we did in 2018, we had calculated a lot of data for group 3 oxides, so gallium, aluminium, indium oxides, and so cohesive energies and band gaps, several thousand. We described these data very carefully and offered them at the Kaggle platform and asked the machine learning community to come up with models to describe the cohesive energy and the band gap. Within 2 months, nearly 900 different solutions by several hundred groups were submitted. And the best performing machine learning description came from a person from Japan. We didn't know this person before. And he came up with a model which we didn't know before. So doing this combination, just accept that there are other people. And in fact, in this case, we learned a new method, which was really fantastic. But there's much more. We are at the beginning, that should be very clear, but we think we are useful already. And just very fast, actually, some examples. Already with the database which we offer, there's no need to repeat computations and increasingly no need to repeat measurements because they're described in every detail. This saves huge amount of CPU times and many working hours. It also implies there is a steep learning curve for students because now they have well-documented reference data, not just a publication, but all the details in the theory, all the full input files. It enables us to do error estimates much better than it was before because we have a much bigger pool of data. And it implies that there is much more data available, which we could use. We could search for results that were computed or measured, but they did not enter a publication because the way we write software publication is that we have a special topic. But of course, some data may be interesting for something else. In this AI concept, with this bigger data sets, it is possible to characterize much better, actually, and describe data, artificial intelligence much better, and to check and benchmark standard and new tools. Now, you know that artificial intelligence and machine learning, I would say, is to some extent overrated. But with these bigger data sets, we could actually be much more carefully look where are the limits, what can we trust, and where should we be carefully? And there is much more. So, FAIRmat, the next thing will be publishing Exploring Data with NOMAD by Markus Scheidgen. The software, NOMAD is the name of the software behind the repository and the archive. And just 1-2 sentences for the finish. An efficient, fair research data infrastructure will enable really a new level of science, as I've tried to describe in this talk. It will bring us to this next paradigm where we describe things in terms of correlations and genes, not necessarily really the exact mechanisms. It will complement, but it will not replace the scientific practice of today. Not replace, but it will be powerful, and we believe that scientists who use such infrastructure, they will replace those who don't use it. With this, I thank you very much for your attention. And with this, I really ask you for questions, and I will try to answer. Thank you very much.